You think you know how the internet works. You click. Something happens. Simple, right? Wrong. Every time you send a message, watch a video, or open a web page, you're triggering one of the most complex systems ever built by humans. A system powered by hundreds of thousands of miles of cables, stretching across continents and lying deep beneath the oceans. A system that pushes your data through dozens of computers, all in the blink of an eye. A system so massive, so fast, and so precise that it feels like magic. But it isn't. How does a video stored on a server in California appear on a phone in Tokyo in less than a second? How does a message find the exact right device among billions connected worldwide? How does data know where to go, every single time? Today, we're going deeper than apps, websites, or social media. We're going to follow the journey of a single click, through cables, servers, signals, and invisible rules that quietly run the modern world. Because the internet isn't magic, it's something far more impressive. The click. Let's start with something simple. You open YouTube and click on a video. That click, that tiny gesture, just started a race. Your device needs to find that video. But here's the problem. That video isn't out there somewhere in the magical cloud. It's sitting on a physical hard drive in a massive warehouse full of computers called a data center. And your device has no idea where that data center is. So the first question the internet has to answer is this: how do we find it? This is where everything begins. With an address. Just like your home has a street address, every device connected to the internet has an IP address, a unique number that tells the internet exactly where to send information. Your phone has one. That server holding the YouTube video has one. And right now, your device is about to send out a request saying, "I need this video. Here's my address. Send it to me." But before that request can go anywhere, it needs to know where to send it. And that's where the real journey begins. But there's a problem. You didn't type an IP address. You typed youtube.com. So how does your device translate that name into an actual address? That's where we need to talk about the internet's phone book. DNS. The internet's phone book. Every time you wanted to call someone, you had to memorize their phone number. No names, just numbers. That would be a nightmare. The internet has the same problem. Every website lives at an IP address. Something like 172.217.1.4.206. But nobody wants to remember that. We want to type youtube.com or google.com. So the internet created a system called DNS, the domain name system. Think of it as the internet's phone book. It translates human-friendly names into machine-friendly numbers. Here's how it works. When you type youtube.com and hit enter, your device doesn't know the IP address, so it asks for help. It sends a query to a DNS server, basically saying, "Hey, what's the IP address for youtube.com?" But here's where it gets interesting. There isn't just one DNS server. There's a hierarchy. First, your request goes to something called a recursive resolver. This is usually run by your internet provider. The resolver checks if it already knows the answer. If it does, great. If not, it starts asking around. It contacts a root server. Think of this as the top of the phone book. The root server doesn't know where YouTube is, but it knows who might. It points the resolver to a TLD server. TLD stands for top-level domain, like .com or .org. The TLD server says, "I don't have the exact address, but I know who manages YouTube's records." It points to YouTube's authoritative name server. Finally, the authoritative name server responds with the actual IP address. And all of this? It happens in milliseconds. Now, your device has the address. It knows where to send the request. But getting there? That's a whole different challenge. The route, finding the path. Your device now knows where the YouTube server is. Time to send the request, right? Not so fast. You can't just send data directly from your phone to a server halfway around the world. The internet doesn't work like a phone call where you get a direct line. Instead, your data has to hop through multiple networks to reach its destination. And here's the genius part. Your request doesn't travel as one piece. It gets broken down into tiny chunks called packets. Think of it like this. You want to send a book to someone, but instead of mailing the entire book, you tear out each page, put them in separate envelopes, number them, and send them all at once through different routes. Some go by truck, some by plane, some take shortcuts. They all arrive at different times, but when they get there, they're reassembled in the right order. That's exactly what happens to your data. Each packet contains a small piece of your request, your IP address, the destination IP address, and instructions on how to put everything back together. Now, these packets need to find their way. And that's where routers come in. A router is like a traffic controller. Every time a packet reaches a router, the router looks at the destination address and decides, which path should I send this down? It checks its routing table, which is basically a map of the network, and forwards the packet to the next router in line. Your request might pass through 10, 20, maybe 30 different routers before it reaches the YouTube server, each one making split-second decisions about the fastest route. And who owns all these routers? Your Internet Service Provider, or ISP, controls the first few. Then it hands off to larger networks, Tier 2 providers, Tier 1 providers. These are the massive telecommunications companies that own the backbone of the internet. But here's where it gets truly incredible. Because at some point, if that server is on another continent, your data has to cross an ocean. And it doesn't fly through the air. It travels through cables at the bottom of the sea. The backbone, undersea cables. When you think of the internet, you probably think of satellites, signals bouncing through space, wireless technology. But the truth is far more physical. Over 95% of all international data travels through cables, massive fiber-optic cables lying on the ocean floor. Right now, there are more than 400 of these cables stretching across the world's oceans, connecting continents. These aren't small. Some are as thick as a garden hose, and they're buried under thousands of feet of water, running along the seabed for thousands of miles. Inside each cable are strands of glass fiber, thinner than a human hair, and through these fibers, data travels as pulses of light at nearly the speed of light itself. Your YouTube request, broken into packets, is now a beam of light shooting through glass under the Atlantic Ocean, or the Pacific, depending on where that server is. And it's fast. A signal can cross the Atlantic from New York to London in about 60 milliseconds. That's faster than you can blink. But here's what's wild. These cables are vulnerable. Ships drop anchors. Sharks bite them. Yes, sharks. Earthquakes shift the ocean floor. And when a cable breaks, entire regions can lose connectivity. That's why there are so many cables. Redundancy. If one fails, the data reroutes through another. Companies like Google, Facebook, and Microsoft have spent billions laying their own private cables because they need speed and reliability. The internet isn't just something that exists. It's something that has to be constantly maintained, repaired, and expanded. So your request has crossed the ocean. It's traveled through routers, through underwater cables, and now it's finally approaching its destination. The data center, the place where your video actually lives. The data center, where everything lives. The data center. This is where the magic happens. But forget everything you think you know about the cloud. There is no cloud. There are just massive warehouses filled with thousands of servers, consuming incredible amounts of electricity, cooled by industrial air conditioning systems that run 24/7. Your YouTube video isn't floating in the sky. It's stored on a hard drive in one of these buildings. When your request finally arrives at the data center, it goes to a specific server. That server finds the video file, breaks it into packets, just like your request was broken down, and starts sending it back to you. But here's the thing. YouTube doesn't just have one data center. They have dozens. Google operates data centers all over the world. North America, Europe, Asia, South America. So why? Because speed matters. The farther your data has to travel, the longer it takes. If you're in India and the video is stored in California, that's a long journey. But if YouTube has a copy of that video on a server in Mumbai, your request doesn't have to go halfway around the world. It just goes a few hundred miles. This is called a Content Delivery Network, or CDN. Companies like YouTube, Netflix, and Facebook use CDNs to store copies of popular content closer to users. The video you're watching right now, it might not be coming from YouTube's main servers. It could be coming from a server just a few cities away. And it gets even smarter. If a video is being watched by millions of people at the same time, the CDN distributes the load across multiple servers, so no single machine gets overwhelmed. So the server has your video. It's been broken into packets, and now those packets are racing back to you. The return journey has begun. The return journey. The packets are on their way back. Thousands of tiny pieces of your video, all traveling independently through the internet. Some take one route, some take another. Some arrive in microseconds. Others take a bit longer because they hit traffic at a busy router. But here's the incredible part. They don't all arrive in order. Packet number 500 might show up before packet number 2. Packet 1000 might arrive before packet 750. And yet, somehow, your device knows exactly how to put them back together. How? Because each packet carries information. A sequence number, instructions, metadata. Your device uses something called TCP, the Transmission Control Protocol, to manage this chaos. TCP is like a quality control inspector. It checks every packet as it arrives. It makes sure nothing is missing. If a packet gets lost along the way, TCP notices and asks the server to resend it. If packets arrive out of order, TCP rearranges them. And all of this happens in the background while you're watching the video. Within seconds, maybe a fraction of a second, all the packets have arrived. They've been reassembled. And now your device decodes the data. It takes those packets, turns them back into a video file, processes the video codec, and finally sends the signal to your screen. Pixels light up, colors appear, sound plays through your speakers. And just like that, the journey is complete, from your click to the data center and back, through routers, undersea cables, servers, and protocols, all in the time it took you to blink. And the craziest part? This is happening billions of times a day, all over the world, right now. So let's zoom out for a second. You clicked a button, a simple action, something you've done thousands of times without thinking about it. But in that moment, you triggered a global system involving millions of devices, hundreds of undersea cables, countless routers, and data centers scattered across continents. Your request traveled thousands of miles in milliseconds. It was broken apart, sent through glass fibers as beams of light, reassembled, and delivered back to you. And it just worked. No one had to coordinate it. No central authority managed the route. The internet figured it out on its own, using protocols and systems designed decades ago by engineers who imagined a connected world. Here's something to think about. Right now, at this very second, there are over 5 billion people connected to the internet. Every single one of them is sending requests, streaming videos, downloading files, sending messages. And somehow, the system handles it all. Every day, we generate more than 2.5 quintillion bytes of data. That's 2.5 followed by 18 zeros. And all of it is flowing through this network of cables, routers, and servers. The internet isn't magic, but honestly, it might be the closest thing we've ever built to it. It's a testament to human ingenuity, to collaboration, to the idea that we could connect the entire world with light, glass, and code. So the next time you click on a video, send a message, or load a web page, take a second to appreciate what just happened. Because behind that simple click is one of the most extraordinary systems humanity has ever created. And now, you know how it actually works. If this blew your mind, hit that like button. Subscribe if you want more deep dives into the technology that runs our world. And drop a comment. Let me know. What part of the internet's journey surprised you the most? Thanks for watching. I'll see you in the next one.